All right, let's take a look. Let me make this a little bigger for you guys. So if we take a look here. Yeah, states of matter, right? Gas, solids, gas. Let's keep that in mind. What things have concentrations? Solutions. What is the state of matter for solutions? No.
Aqueous.
Yeah. So that has concentrations and like moles per liter. And gases have concentrations like moles per liter. Liquids, not so much. So liquids are just sitting there. Let's just imagine that this is a pure substance. Not really a concentration. It's there or it's not. Solids, same thing. So we will be ignoring liquids and solids in a lot of these reactions when we're solving for equilibrium. The other thing that we need to see is this arrow. This arrow goes forward and reverse. We discussed this concept a little bit last time whenever we talked about the forward reaction rate and the reverse reaction rate. This can be easiest seen not looking at a reaction, but looking at a saturated solution. So here we have a saturated solution. You can see that solid, like kind of floating around down at the bottom of it. That solid is not the same atoms that it was 2 days ago, right? So let's imagine that this is just sodium chloride. I'm not sure what it is. Sodium chloride solid will become sodium ions plus chloride ions. Yes, yes. But since it's saturated, it means that no more can actually go into solution. Well, imagine on that sodium chloride repeating pattern. Right? Imagine all of a sudden a sodium joins here from the water. It's attracted to that solid to form that crystalline pattern. Well, now is it a saturation if a sodium just joined onto the solid? No. So that means that a different sodium could do what? Could leave and become aqueous. So what does that mean? Well, that means that this is constantly changing, right? If we look at it on another day, the atoms would be totally different in that. What is the term for changing?
Dynamic.
Yeah, somebody just gave me the mathematical symbol, not mathematically. What was said at home?
Dynamic.
Yeah, dynamic. If you ever been studying a character in English, did you say it? He's taken English class before. What's the character that does the changing in the novel, right? That's the dynamic character, means changing. Ozzy, what? What? Oh. So the dynamic character in the book is the one that undergoes the changes, right? So this is changing, but it's staying the same. That means the same amount of or ratio of particles dissolved and particles not dissolved must remain the same. Does that, they must remain the same. That doesn't mean that the number of particles dissolved is equal to the number of particles not dissolved, right? But the ratio of dissolved to not dissolved must maintain the same because that's the saturation point, right? So we call this equilibrium, right? It's just like the equilibrium that you're in your mind whenever, that allows you to stabilize yourself or whatnot. The same thing happens with these particles. They maintain that ratio, right? So it's a changing equilibrium or what we call a dynamic equilibrium. Yeah. All right, so let's take a look at this. Let's imagine that we have, and you guys won't be able to see this at home, I'm sorry, but let's imagine that we have these three desks and they are conjoined, right? All of a sudden, this desk comes in. This desk leaves, and this desk joins on. The ratio of joined desks to not joined desks is still the same, right? But is that the same three desks we started with? No. Are they equal? Are the number of joined desks equal to the number of non-joined desks?
Oh, I thought you had 1.
But that's what I mean. But the number of the 3 and 1 are now equal to each other, right? Yes. So that's equilibrium still, but it's dynamic equilibrium. It's the ratio of 3. They are 1 to 3. And it's still 1 to 3 after the thing. That's what we're saying. It's not, it doesn't have to be. The ratios just need to maintain equality. So the 1 that's still by itself is still 1. Even though it's a different one, it's a different desk, right? The 3 that are together, it's still 3 desks together, even though we have a different one. But it's still holding that equality of 1 to 3 ratio, but one of the desks is different. Huh?
I get it.
You understood? Now you're confused. So again, this salt, right? Sometimes some of these particles come off and another one has to join. But look at the number of particles here. It's not going to be the same as the number of particles around. Yeah, we lost Owen. Maybe we'll pick him back up at some point. Because he never talked on the thing? Because he never talked on the thing?
Yeah.
You have a question or just? Yeah, go for it.
So why do the atoms
That's the thing, because there's going to be all these micro attractions and stuff like that, right? Because the water molecules are polar. So they're going to, if they can get close enough, pull off some of these sodium chloride ions. If some reattract, and the sodium chloride itself is going to be able to attract some of them, right? Because opposites attract. So if some do get attracted, then that means that there is room now in solution for some more to dissolve, right? And so it's just this pattern that keeps going. Above, yeah. Slowly return them, yes. Stabilize them, like in a fashion that doesn't cause disruption. Yes.
So how?
Basically, you get the particles up to a high enough temperature that they are able to dissolve, and then you kind of trick them into staying dissolved by just lowering the energy, but not having any major disruption that causes the first crystallization. Because once the first crystallization is formed, then it's going to cause that repeating pattern to just go blah, 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 blah. Yeah. All right, so there still is a little bit of confusion with the dynamic equilibrium. So let me try something else. I don't know. We did. So if we take a look, there are 3 balls there, and there are 3 balls here. Actually, let's do this. Let's put 4 balls here. Are we laughing at something immature? So there we have 2 groups, right? What's the ratio?
3 to 4.
3 to 4. So we have 3 to 4. So let's say that these 2 switch. Is that dynamic? Did it change?
Yes.
Did the ratios change? No.
No.
Let's imagine that these are reactants and these are products. Did it change?
Yes.
Did the ratio change?
Nope.
No.
Are we good now, Owen? All right, good. Good, good. So that's what's considered dynamic equilibrium. So you have what we call products and reactants, and you have a reversible reaction. Right? So here are the reactants and here are the products. We are going to develop what's called the equilibrium constant. The equilibrium constant K is equal to the ratio of products to reactants. Brackets refer to molarity concentration, right? And it's per liters. So if K is 1, then that means that the ratio of products to reactants is what? 1 to 1. If K is greater than 1, that means we have more what at equilibrium?
Okay.
Products. And if K is less than 1, that means we have more.
Reactants.
Good. If K is 10 or greater, that reaction pretty much goes to completion. Completion means that we have so much products to reactants that the reactants are kind of negligible. If K is, what is it, less than, it's less than 1, it's reactant, but it's like, if it is, I think it's 1 times 10 to the, like 0.001 or something like that. If K is less than 1, or let's just put less than or equal to 0.0, maybe 10 to the 4th, 0.1. 10 to the negative 4th. And I'll have to recheck on this, but this will give us a good start at least. Then that means that the reaction almost doesn't go at all. Right? So out of 1,000,000, maybe 4 or something, like something ridiculous like that. That just gives you an idea of how K works. Now let's see how we set it up. When we were dealing with our rate laws, we dealt with K. That's a little bit different. That's a rate constant. This is a constant of equilibrium. These are 2 different Ks. All right. So if we take a look here, K sub EQ, which is the equilibrium constant, we also can just abbreviate that as K, is equal to the products PCl3, Cl2 over the reactants, PCl5. Again, brackets showing molarity. Easy enough. Yeah, you know how this always is. It starts off real easy, right? And then by the end of the period, I'm standing on my head and we're on page 5 of it. And we're talking about globotrons. No, I made up globotrons. They invented them. That's how cool they are. They're inventing stuff now. All right, so what is different between A and B?
You have 2 O2, so you have to put exponent.
We have 2 O2s. So let's take a look what that means. We have products into O4 over the reactants. We have into, and then we have 2 O2s. And most of the time, we would not write it like that. But that's what that means, right? We can do O2 square instead. Because for every 1 mole per liter of this, we have how many moles per liter of this? 2.
Dose.
Dose. Who was that? Was that Noah?
That was Noah.
That was Noah. Actually, are you bilingual is the question in the classroom. Yeah, right? That's what I'm expecting too. No.
I take Spanish.
You take Spanish, so you could say
No,
that.
I take Spanish.
Oh, Noah takes Spanish. Noah? This is all Noah.
Wait, why is it going?
He's,
Not all know it.
they didn't even pay attention. I told you, he told us he was sick. He wasn't feeling up to par. Noah, this is why teaching online is so difficult.
Yes.
Noah, they miss you, they said.
I
Gavin,
miss you guys too.
what's
I
that?
miss you guys too.
Oh, he misses you guys. All right, so can you do C on your own?
My dad laughed at me.
About what?
I said I miss you guys too, and then he laughed.
Funny? He probably laughed at thinking it was, he probably laughed thinking it was cute. It is cute. But it's also the degradation of audio quality from the, yeah. Yeah, you guys all sound the same on there to me. Yes. You guys all sound like kids. Yeah, go ahead.
So you're not calling it, he never.
Nobody raises their hand and gets called on in here. You guys just blurt stuff out and then I answer it.
Do you want me to do that?
I don't care.
Okay.
That doesn't mean you can just constantly talk, Leo. I know.
So aqueous solutions
Yes,
are in water.
they're dissolved in water. That's
Why
what.
don't we include water?
Because all water is, it's non-reactive in it. All it is a method of getting the particles spread out so that they can collide more.
But why don't we put it in water? I didn't ask you.
AQ actually means that it's in there, but it's not, it's a spectator.
Okay, I want to. How can something go from aqueous to solid?
By vaporizing off the water,
But why don't we include the water?
because that's why we call it solid and not aqueous anymore.
Where is it?
So aqueous means like ions dissolved.
Evaporation, but into the air,
No, but where is it?
into the air.
But those shouldn't be included though?
No,
But it's in the, it's still.
it's not part of the reaction.
That's not very funny.
Owen has that way. What? Oh, no. Is that you that said that? Sorry. What's the rest of the question, buddy?
But it's still part of it. I don't get why we don't include it.
It's part of the universe, but it's not part of the system.
But it is part of it.
It's not part of the system that we're looking at and interacting with.
Why is it-
Yeah,
Yeah.
I'm not part of your system.
But we include it in the ones down here. In C and E on aqueous,
Where?
C and E with aqueous. We include it there.
That's because those are acid-base reactions. So hydrogen is a huge part of acid-base reactions. So water is actually being broken up into hydrogen plus and OH negative. That's why we need to include it.
Oh, he's on, oh, okay. Yeah. I'm on the same page.
Ready? Yes, equilibrium constant. Did you guys get it? NH3 to the what? Second power? N2 to the what? 1 power. And H2 to the what? Third power. What's different with D?
Yeah, the solid.
We have a solid. So as we said, solids and liquids do not have concentrations. What do the brackets mean? So solids will become 1, which we don't need to include
Why are they not? Oh, because they're all,
because they're present.
that makes so much sense.
Good.
Because they're all meters.
It's not moles per liter. It's just one thing. It's present or it's not.
Like that.
So that means that E down here, you would have K sub EQ equals what?
Why don't we just know?
Just C2H508. That's
There
it.
you go. You may not. You may not need to know it. But some people may in the future. You're gonna see that whenever we do the quadratic stuff.
Okay.
You can see how powerful this is. For Monday, complete this
Oh, it's the same one.
because it's liquid, so it's over 1.
Wait, oh, it's not.
Well, that's an L.
Talking about the state of matter of this. So let us put some math to it. K sub EQ, we did this one just a few seconds ago. We have HI up top to the square, and we have H2 down at the bottom. Who are we not including?
The iron.
Iodine.
Solids, I like the singing. Yeah, right, the iodine, that's a weird bracket. And then we will take and plug in 0060 for HI. Oops. Squared. And then 0.015 for H2. 0.060 squared divided by 0.015. And then it's refusing to do it, so. 0.240. Is that what you got?
Oh, no, I did it wrong.
0.24. Yeah, actually, to tell you the truth, I did it the opposite last time because I read this first, so I just put it on top. Yeah. So is this favoring products or reactants?
No.
It's less than 1, right? Cool. So that's about as easy as it gets. I'm going to give you about 3 minutes, 4 minutes to work problems 2 and 3. Question, Brody?
Keep patting me on the back.
All right, so what's weird about this one? We are solving, hopefully the algebra did not fool you on this. So we have K sub EQ, products over reactants. Well, you algebra differently than me. Remember, I am weak on math skills, so I have to do everything like this, not much in my head, right? So if I'm setting this up, but I'm trying to solve for HNO2, what do I want to do to both sides? Multiply by HNO2 and divide by K sub EQ. So we get that right there. And I assume this was Claudia. Did you take one of my Hershey Kisses as well?
Wait, you are.
Sucker.
Ah,
Ah. Would you have just taken it, you thief?
I probably would have. I've been.
Question, is LSD actually acid?
Yes.
Oh.
For experimental purposes?
I just think it's a work.
And then we divide by the K. Let me ask you this, is the products or reactants favored for this reaction?
Reactants?
0.0071.
Point
Wait,
zero
Mr. Jackson.
squared divided by 0.00071.
It's the products because it's above. One.
No,
Wait,
struggle bus today.
what did I do? Wait,
It's kind of cool. What happened?
Yeah, I think kind of slacking.
Did you guys mute him?
No.
oh.
Did they
Oh,
mute you,
well,
Akshay?
How could we mute him?
Oh,
Well, you drew this thing. I didn't know what else you did. What did you say? What did you say, Helen?
He said,
Yeah.
Did you guys get 0.5? 0.51?
actually,
yeah.
yes. Of course, that's exactly what I got.
Figured it out.
What did you get? That's exactly what you got. Good.
No, I was okay. Never mind.
Wait, Mr. Jackson.
Yes,
So you said that if its K is less than 0.0001, then it should be favoring the reactants, but in the first one, it's 0.24. So how would that favor the reactants?
if it's less than 1, it favors the reactants.
Okay, and if it's greater than like
Greater
10,
than- Yeah, just think of the 1. Don't focus too much on that 10 and stuff like that. It's best to just focus on 1. If it's greater than 1, then it favors the products. If it's less than 1, then it favors the reactants.
okay,
When things get heavier with these reactions and stuff like that, then you can sit there and like even in acid-base chemistry, and I don't know if we'll get into it in next chemistry, but whenever you start looking at that, that's what determines whether something's a weak acid or a strong acid.
yeah.
It's a weak.
It's really sweet.
Yeah, but you don't know what strong and weak means yet, though. Yes, Brody. It doesn't deal with pH. Strong and weak doesn't deal with pH. Down here? No, we'll get to that one in a second. What I do want to show you is that this is actually an acid. This is nitrous acid, and it is a very weak acid. So that's why it has such a small K. So if we have 0.019 of each of these, notice that as this reaction goes forward, we're going to get the same amount of this as the same amount of this that forms, aren't we? So at equilibrium, we have 0.51, and this does get a unit, moles per liter, of the HNO2 compared to the 0.019 of H and 0.019 of NO2 moles per liter. Consider the aqueous equilibrium here. The question in class was, do we have to figure out the molarity of the AlOH3? Brody, do you want to tell us why we don't? You got it, sir.
Wait, Brody's in class?
Oh, so we divide by.
Yeah, Brody's in class. He's been in class.
Then
Huh?
why is he on the Zoom then?
That's the way he rolls.
Oh, I didn't know that.
Does that mean you're going to try to do that now and be on the Zoom while you're in class?
No, probably not.
We have Brody sitting all the way in the back of the room, so this is better for him.
Oh, yeah.
So what are we going to put on the bottom of this, Brody? 1. Now let me ask you, this is actually what Claudia was talking about earlier. Look what is actually happening here. We are taking solid aluminum hydroxide, and we're breaking it off into aluminum and then 3 hydroxides, right? So that's pretty cool when we think about this, because this is exactly what we were talking about when we were talking about the solubility table. What does the solubility table tell you? Whether something can dissolve or not dissolve. We'll take a look. Is aluminum considered to be soluble?
I can't do anything else.
I know.
Can't read that.
Yeah, it's on the back of your periodic table. Is aluminum one of the ones in the soluble? No. So that means that aluminum is insoluble. So you might have thought that that meant that it did not dissolve at all. In reality, that means that it doesn't really dissolve well at all. So let's take a look. What is its K?
Very low.
Very low, right?
Very.
Very, very low. So that means a small portion of it may go into solution. But compared to what you have, almost nothing, right?
Is there anything that's like not soluble?
I mean, this is pretty close at 1.9 times 10 to the negative
Yeah.
33rd, but yeah. So this is, yeah, like, I mean, if we go with oil, or, you know what I mean? Like, it's not water soluble. What, to tell you the truth, water is what you could consider soluble in water, but that's the next unit. So if we, and it's called water dissociates water.
Wait, do you ever learn about the so,
The soda machine?
yeah, the carbonator?
Yeah, we did. Solutions unit. AL3 plus is, that's what we're looking for, huh? So normally I would do what? Let's just maintain that I keep doing the same things that I always do. What are we gonna do to both sides to get this? We're gonna divide both sides by OH negative to the third. So that equals our, that would cancel out there. That equals our K, which is 1.9 times 10 to the negative 33rd. Divided by 8.7 times 10 to the negative 9th. That's why I always press it down first. It's not wet white out, it's this stuff. Correction tape. You gotta press it down first.
I always thought it was
Yeah, right. No worries. Do you guys find that you are talking more than you normally would during a class now that, like, since there's less people?
Yeah, this class is
But
so
only English,
fun.
every other class.
Like something about this room makes you just like blah, 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 blah.
I don't know if it's something to the last period, but it's kind of the lower one period.
Ah,
It's a people in class.
yeah, I tell you, the dynamics of these classes that I have this year are pretty awesome.
I don't know about 5, 6.
Well, I mean, 5-6 is the coolest.
I think
Dynamic, I know that word.
What's that?
You said dynamic.
Yeah, the dynamics of this class, the changing. So if we take a look, we get 2.18 times 10 to the negative 25th moles per liter for that. Well, let's do this. For every 1 mole of aluminum, how many moles of hydroxide do you get? 3.
Wait, Mr.
So
don't you
let's-
cube that.
Oh, dang it. Yep. Thanks. I forgot to cube it. That means this is going to be wrong. So I'm going to give everybody, what did you call it? You get apprehensive whenever I do this. And then you just tap it. It's like I never made the mistake. What did you say? I'm gaslighting you? 2.9, is that what you got? 2.9 times 10 to the negative 9th molarity?
Yep.
Yep, thank you, actually. So if for every 1 mole per liter of this, we get 3 moles per liter of this, then if we multiply 2.9, if we multiply this times 3, we should get 8.7 times 10 to the 9th, right? Because the concentration of this should be 3 times as much as this. You okay? All right, so that gets us a lot of the K sub EQ thing. Now we're going to bring in what's Q, what's called quotient. The quotient is the same expression as K sub EQ. So it's products over reactants. K sub EQ is only at one time during the reaction. And when is that? At equilibrium. Was that Claudia? Right. Nice. As Claudia said, that's at equilibrium. So what does that mean? It's only one part of the entire process of the reaction. It's when it reaches equilibrium. Q can be at any time. So Q could be right at the start, or Q could be somewhere, past equilibrium, or whenever we change equilibrium by doing some little thing to it. So Q can be anytime. So if we do this, nothing to square 0.25 times 0.1 divided by 0.005.
It's 5.
5. What's that? calculator, can't use it. So it's 5. If K is 150, where are we compared to K?
100, right? One.
You might have just blown my math brain. Give me 1 second. We are either above 150 or below 150? Below 150. So Brody asked a good question, and I answered it as I was running out of the room. Brody said, what does this number actually mean? Well, basically, we can look at it as a ratio of the concentrations of products to reactants. So right now, those ratios are 5 products to 1 reactant. At equilibrium, it should be 150 to 1. So are we at? No. Are we below? So we actually need to make more products to get to 150 to 1, right? So which reaction would be favored? The forward reaction, which makes phosphorus trichloride and chlorine gas, or the reverse reaction that makes phosphorus pentachloride? Well, there's 2. There's the forward one or the reverse one. What does the forward one make?
Products.
Products. What does the reverse one make? Reactants.
We need more products.
So we need more products. So which one are we favoring?
The
Forward. Let's not use first and second. Let's use forward and reverse. So yeah, Akshay said here, forward, 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 and you guys are like, wait a second, what? Yes, the forward reaction would be favored. Yep. So we have Q, right? So it says here under part C, you calculated Q equaling 5. You concluded that the reaction was not at equilibrium because Q does not equal 150. We are much less than a 150 to 1 ratio. We are 5 to 1. How can we get closer to a 150 to 1? We make more product. What makes more product? Forward reaction. If Q is less than K, forward reaction favored. What if Q is greater than K? That means we have too much product. What do we have to do? We have to make more reactant. And in reality, when we make more reactant, what do we use up? We use up product when we make reactant, right? Good, good. Go ahead and take a second to do this one, please. Ooh, am I gonna have time? I'm not gonna have time. Do this one on your own, and then Monday, I will post the answers up to this page. Keep in mind, we are on easy mode right now. If you don't do this homework, when we get to hard mode, you're gonna be done. That's how fast this stuff switches, right? Stoichiometry, right? Yeah, well, I mean, when we go to stoichiometry, you just learn how to do the moles. So if you did not learn how to change the moles and all that, then you can't do stoichiometry, right? That was you? Yeah. That's all I've got for today, guys. If you have a question, by all means.
So every time it's like, it's 5 minutes.